Aerospace is a weird industry in that everyone is there because they are gigantic plane/space dorks. And I'm not really any different. This is a thing that I always thought was incredibly exciting. And I don't know that there's a culture on Earth that hasn't told stories about the stars. So I know that I'm not alone because people always want to look up.
Most robotics demos never ship. Deployed is about the ones that do. This is Deployed, where physical AI gets real.
I am super excited today to welcome Scarlett Koller as my guest on this podcast. Well, let me give your background a little bit. So Scarlett, 3 MIT degrees, Amazon Prime Air, Amazon Kuiper satellite program, SpaceX Crew Dragon, NASA Perseverance, and now with your own space company, Mithril. Mm-hmm. Amazing career, and I think very directly tied to what it actually takes to deploy systems in the real world, right? Mithril's fascinating, we'll get into it. We'll get into MIT LGO a little bit. Jeff Wilkie, a previous guest, is obviously LGO. Bilal spoke a lot about investing in deep tech. So you and I first met, I think, here at MIT, interviewing for this crazy internship program that we had decided to do, where the Amazon Prime Air program, we had just gone on 60 Minutes in November, announced this drone program, and then we were trying to figure out how to staff it. And I remember talking to someone who'd been on the Stanford DARPA Grand Challenge project for autonomous vehicles, and I asked how they staffed it, and they said we started with 60 people to explore the whole space, and then we dropped down to 12 people to actually build it, which I thought was fascinating. So we had this idea, let's bring an intern cohort together, let's get 19 interns to explore all the ideas we have for drone delivery. And then we came to MIT and just interviewed a batch of students from AeroAstro, from mechanical, from computer science, and you were one of those.
Yeah.
Interviewed, got the opportunity, joined a cohort. We started everybody on the same day. But I want to hear that story, like from your side. Like, how did you find out about this crazy internship program? I believe you were a sophomore at the time.
I went in to interview with a good friend of mine, and we ended up rooming together over the summer. That was Burke, if you remember him.
Mm-hmm. Yeah.
We were still good friends, actually. He ended up marrying one of my really close friends at MIT as well. He's at MITRE now. He finished his PhD a couple years ago, so he is doing awesome, by the way. Yeah, I want to say maybe he told me about it. I don't remember. I do remember the interview because I talked to your colleague Daniel Buchmüller.
Yeah.
We got along very well. I actually should ping him on LinkedIn. And your context for, okay, well, let's just bring in a bunch of interns, more than we need, so we can explore all parts of this space. That's actually making a lot of sense now for what we ended up doing, because that is what we ended up doing. You guys gave us, I don't know how many drone kits and prototyping shop and resources and a flight cage, and kind of broke us into teams, and we're like, do wacky things with drones. And that was almost it. I mean, you guys were, it did feel in some ways kind of like throwing spaghetti at a wall and seeing what stuck, which is all well and good. I mean, the 60-minute segment was really cool, and it was also not really representative of challenges that any drone delivery system would actually have to overcome. So yeah, I will say that was a really, really fun experience. I was a little nervous. It was my sophomore year. I wasn't sure of myself in the interview. I did learn a lot over the summer. It was a really, really valuable experience, and I think being kind of turned loose, as it were, was really helpful. We came up with a lot of wacky things.
In doing the research, I realized you got a patent out of that work.
Yeah. So we realized, okay, well, if you are lowering a payload from a drone, so that's your drone delivery, that creates a ton of instabilities in the system. And zooming back out, by the way, what we also realized was, okay, we have a flight cage here. This is, plexiglass, so that nobody can get hurt by the propellers. How are you going to deliver these things to regular human beings who have kids and dogs who are going to want to mess with it? All right, don't land the drone. Just lower the thing. And then that was pretty interesting because we realized, all right, this is actually a pretty difficult problem. The dynamics of that system are wildly unstable. It's functionally a double pendulum disaster. And how do we even begin to overcome that? And what we realized was, well, okay, you're always trying to do it with just a dumb payload that you are lowering on a cable or a set of cables, and you have an active rotorcraft that you're trying to lower from. Well, what if you made the stabilization active, right? What if you are kind of constantly compensating? And I'm not saying you can always get it to be perfectly stable, but we're in at the very beginning. As I said, this was my sophomore year. I had just barely learned what a PID controller was. And you can get it good enough with PID control to implement self-stabilization on that payload so that you can lower it to the ground without just knocking your drone out of the sky. And I don't know if that ever got used, but it was a cool piece of work.
Well, so the fascinating thing, so the whole idea of doing this exploration was to train our intuition as to what might work or not. And yeah, I still remember you had like a dual drone system with a drone above and a stabilizing payload, and it was amazing. When we saw the Google Wing video come out, where they did tether drop, we saw something in that video that other people wouldn't have realized because we had done that work. What we noticed is they got around that problem by just dropping really fast, right? They just like plummeted the payload near to the ground very quickly, and then caught it like right before the ground, and then kind of let it go.
I'm now having visions of the Mission Impossible scene.
yeah, exactly. But who knows how many videos they took where it hit the ground, right? Maybe take me back a little bit. Like, how did you get passionate about aerospace, space, or just tech? Like, what brought you to MIT? What's the backstory?
The space stuff has sort of always been a thing that captured my imagination. And I also was just really, really egregiously stubborn. I'm still egregiously stubborn. And I wasn't really listening to anyone who was like, have you considered, being a doctor or a lawyer or something normal?
It's interesting. I came to MIT thinking I was going to go aeroastro because I grew up less fascinated by space, more fascinated by things that fly. Kites, boomerangs, gliders. Professor John Hansman was my freshman advisor. And basically, he kind of illuminated nothing was happening in aerospace. No one was building new. Like, Clinton had kind of shut down. The Cold War was over. There wasn't new rockets being built. The shuttle program was kind of on mothballs. No one was building a new commercial jet. And he was like, how interested are you in avionics? And I'm like, well, if I'm going to do avionics or flight control systems, maybe I should do this internet thing. And so Prime Air was my opportunity to get back to this passion I have. And I mean, I still fly all kinds of RC gliders. And
is that why Amazon tapped you for this project?
For the Prime Air drone, that's why I raised my hand. I'm like, I want to help.
I love that. See, we all love this.
But it was a crazy idea to bring 19 interns together with no support, no structure. And I also remember we had this beat up old building in South Lake Union with no air conditioning. And it was brutally hot in Seattle that summer. And so everyone was just sweating.
No, I remember that. And we had the air conditioning upstairs in the one office area. And we'd go and just stand there.
Yeah, these little portable air conditioners. And then I think the circuits would trip. And it was a mess that summer. But, a lot of science got done. Everyone who's gone through LGO raves about it. It's a very different program than most kind of MBA programs. And so, for our audience who maybe doesn't know about MIT LGO, both I'm interested in your story, why did you pursue it, but also what's unique about the program and what did you take from it?
I'd heard about it in undergrad. I was in the Gordon Engineering Leadership Program. I'm really grateful for that experience, actually. That was the thing that helped me kind of get out of my engineer mode and start actually talking to our NASA counterparts to understand what are the concerns that you have, because they're behaving differently. They have different incentives. It's a different environment. So I now spent 5 years kind of learning how useful is the GEL program, which had, and when I was an undergrad, I had a mentor in GEL who was from LGO, And so I knew about the program from that. And then, even when I was at JPL, I was seeing, okay, well, first of all, everyone is working remote. We are on mandatory telework. I would be in the test bed at least once a week to physically reconfigure stuff and wiping everything down with alcohol. We've got...
This is during COVID.
This is during COVID.
Yeah.
We are landing something on Mars with everyone working remote and people in masks in the flight ops center. But I was also seeing, okay, well, people are making different decisions depending on the interpersonal dynamics in the room, despite the fact that these are incredibly smart engineers, but they are going to operate differently. So, Al Chen and Adam Stelzner have gotten a certain amount of fame because they're the guys who invented the sky crane maneuver. I worked a bit with Al because I worked with the EDL team. I was over in the test bed puppeting around and creating plausible, realistic, real-time anomalies that they would have to deal with. And if Swati wasn't in the room, sometimes her colleagues, who were all incredibly brilliant, didn't trust themselves sometimes to make a decision, even if they'd arrived at the correct conclusion. Sometimes the anomaly resolution team would all get in a room, and Al would be in there, and because he's the guy who invented the sky crane maneuver, talks a lot. They don't make a lot of progress. We actually created a personnel anomaly in which Al was out of reach for a period at the beginning of, what was the end of one of his shifts, I forget, which is plausible, This
is a test. Presume the leader is unavailable. You can't ask. You can't ask the expert.
Right. We would, there were technical anomalies we were creating, but we would create personnel anomalies, and it's very reasonable. Lots of areas, especially where people were living, there wasn't great cell phone coverage. If you get a flat tire in the wrong place, it's fine. You might not be able to reach that person. And that changed a lot of the way people work. And that was really starting to cement things for me that, okay, I want to understand how is it organizations drive the way people make technical decisions, because there's no such thing as a purely technical decision. And that's ultimately what led me to apply. Now, I will say LGO is the Leaders for Global Operations. I didn't have a correct understanding of what was meant by operations when I applied. I didn't have a correct understanding of this when I interviewed. I'm over here being like, yeah, operations. That's what we do in the Flight Operations Center, where people are figuring out how to send commands to the spacecraft to correct a certain state.
Right.
I everything I'd ever worked on, we built single-digit numbers of it. Except for the drones, and I think we may have built 10 drones. We might have tipped over. Even at SpaceX, where they were churning out a lot of Falcons at the time, and now they're obviously churning out tons of Starlinks. I hadn't given that much thought, but I was really lucky, and I got back in. And as I said, the MBA program was really, really useful for me because I just really did not understand anything about business. I think that was very eye-opening for me. It was really fun for me to realize there were a lot of people here and I'm like, oh yeah, they're just kind of chilling because they know this. All right, people study finance. All right, sure. And that was something of a revelation to me. I'd forgotten that people who weren't engineers existed, and I think it was a super valuable learning experience just to understand, well, what is a business. You and Bill all touched on this. What is a business? What is a product? And I'd never considered that. But then LGO specifically, that's a dedicated group of people. The operations really focuses on, in some ways, focuses on manufacturing. It focuses on supply chain. But it's ultimately, in my opinion, it kind of comes back around. It's still systems thinking.
Yes.
It's still...
Yes. Jeff Wilkie talked about this too. Yes, absolutely.
No, Jeff, I think, Jeff gave us a couple of guest lectures, and I briefly talked to them, and I think we came to the same conclusion of, okay, well, how does this work in the context of this other thing? How does this integrate with something else?
Right.
It's all understanding your dependencies in an integrated system. And so it ultimately did end up coming back to something that I did understand. And that was really, really fun for me.
So take me through a little bit. I mean, Amazon Kuiper, Northrop Grumman, NASA JPL, SpaceX. not that many people have worked under like a Jeff Bezos system and an Elon Musk system and a NASA system. Like, I'm very curious what you see as like the common threads, but also what you see as different. What's real and what's legend out there? SpaceX is legend for like just trying things, but is that really how it works? Like,
at SpaceX, it very much depends what it is you're working on and whom you're working with. There's a lot of claims about flat hierarchy and anyone can volunteer an idea, and in practice, that's not how that shakes out. What it ends up meaning is that the people that you work with and whomever you answer to will have an outsized impact on how you work. And I had this very unusual position because I was a certification and test engineer with life support systems, but I was embedded in that team. I also worked with people in mission management. The people I ultimately answered to were our customers, and that was NASA commercial crew. And these were all shuttle alumni. They'd literally written the book on human spacecraft, and they'd also seen everything that can go wrong, including a lot of stuff that most people wouldn't know about because they were near misses. And to their credit, they'd written the requirements pretty well, in my opinion. The folks who were there to work with SpaceX were very on board with, okay, SpaceX is not going to work the way Boeing does. SpaceX is not going to work the way a lot of our other contractors do. And I'll give this to them. This is 10 years ago when I started there now. They were also a little bit wary of SpaceX acting too cavalier with their people. And they weren't wrong in that respect. And they really pushed a lot of what I would call kind of underrated systems thinking. And again, this varies tremendously at SpaceX. I was actually interviewed for Falcon 9 integration and test. I wound up at Crew Dragon because of an undergrad project where we'd had to file a waiver it was a NASA student challenge, and we had to file a waiver for a pressurized volume. And they said, great, fight with NASA for us now. I'm like, hold on. It wasn't that much of a fight. They have needs, we have needs, they have a risk tolerance, we have a risk tolerance, we have to understand each other. And I think that the SpaceX mentality was not really initially well suited to that. And there are a lot of people who were, chip on their shoulder about, we're not like traditional aerospace. And, we break all the rules. And if you have too many rules, you can't get stuff done. Well, yes, fine. If you do, you can't get stuff done. Absolutely valid. Nobody who worked on the shuttle program and was then on commercial crew was stupid. They were all coming to us saying, look, we actually know that it is not possible to meet every single one of these requirements to the letter. We know that. What we want you to understand is why they were written the way that they were.
Right. The kind of certifications, regulation, testing, to me is about, we get on planes every day and trust that they will get us to the other spot. Flying a plane there are plenty of things that can go wrong, right? Yeah. And yet tens of thousands of flights happen every day and go off smoothly, and it's because we've learned all of these lessons, right? And if you can have access to the people who've learned the lessons versus just the written down codes that don't have a story behind them.
Oh, that was immensely valuable. I mean, if we just had the requirement, it's so easy to say, oh, there are too many requirements, there are too many regulations, if you are looking at them on paper. It is so much different if you are talking to the person, where we had an issue once where the handles on the lithium hydroxide cartridges for scrubbing out CO2, the folks at NASA were taking issue, well, you haven't actually proof tested the handles. We're like, well, you don't have to, mechanical systems, you can qual by analysis. And they kept pushing on this, and we were saying, well, we're not over here gonna do a qual test on this. This is ridiculous. It's a mechanical system. It's already overbuilt, and we have one in the buck where we've moved it in and out a bunch of times, and so it's been actuated more cycles than it ever would be. It'd be fine. At some point, and I'm glad that I cottoned on to this, these are incredibly smart people who are asking us a question that we think is stupid. There is something missing here. It's not because they're stupid. It's not because they're old. It's not because they're set in their ways. So I pulled one of my NASA counterparts aside and I said, all right, let's talk. I'm trying to understand, why is this a problem? Why are you guys focused on this? And we go for a walk and he explains, okay, on one of the shuttle LiO cartridges, it's got a powder in it, right? And we had an issue where someone pulled too hard, it broke the handle, which cracked the canister, which released LiO powder into the habitable volume. And that stuff is toxic. And if you have powder floating around in 0G, it's very easy to inhale. Now, that was a near miss. They cleaned it up. Everyone got their masks. Everyone was fine. No one ever heard about this because it didn't hurt anyone, but it could have. And that was the point where we realized, we've been talking different languages. And that was really, really impactful to me because I think there's a lot of, especially in new space, just kind of, not trying to do it like the old way. And, I think that's valid, but you have to understand, well, why did something happen the way that it did to begin with? And then you can start differentiating. And that's also its own flavor of engineering. It's knowing which parameters you can safely vary. And that, that happened a lot less at JPL. I will say that. So at SpaceX, there was a lot of, because I was a certification engineer, I ended up having to figure out how do we qualify for flight all of our hardware for life support and thermal controls. I shouldn't have been doing that job, not all by myself. It was a wild time. At one point, I had to make people test out a diaper. Had 2 interactions with Victor Glover, who's now getting a lot of press time, and those are the interactions, so I'm really hoping he forgot them. But it was a lot of figuring out, well, how are we going to actually test it? And what does it mean to have tested it in a way that shows that it'll work in an environment that is not this one? The NASA guys had written a book on that. They understood what test engineering meant as a discipline. I think at the time, SpaceX wasn't as sophisticated in its understanding of test engineering. I have to say, I was given a tremendous amount of freedom to learn that. And, it took me a while really to sort of formulate that in a way that my colleagues would understand, because a lot of them were more on the design end and they were doing a lot of dev testing, which was great. And I was saying, okay, well, now we have to take the dev testing culture, which I think is incredible, and roll that into, well, how do we now use that data and to craft a test that will be rigorous, that will be a run for record, that will prove we have done the right thing. And I learned about verification and validation. Verification is, did we build the thing right? Validation is, did we build the right thing? And that was really useful. I found that was super helpful when I then left and went to JPL, because I was an integration and test engineer. I was a test bed engineer specifically for entry, descent, and landing. So that's a whole integrated system test and you have to operate the test bed with all of the brains and guts, all the hardware broken out, except for explosive bolts and stuff that can't be reused, and go through the EDL sequence is 6 days long, and you have to jump forward in time, and it has to be able to do a lot of this autonomously. So when you're operating the test bed to do it, you're very often creating the whole sequence of events in advance and creating that as a test case and setting it up. And then if it doesn't work, you have to watch the rover and all the brains, and you have to watch the simulation support equipment just fail, right? You have to watch it crash into a virtual Mars. And you have to understand after the fact where everything shook out. And you have the added problem of, all right, well, some of the simulations are not exactly like Mars. Who knew? Some of our canned environment is not exactly like Mars. Is this an idiosyncrasy of the testbed? Is this an idiosyncrasy of the simulation? Is this an actual problem that we've identified by way of this test? How do we prove all of those things? And so coming out of SpaceX, I was really grateful for the mentality of, well, keep testing it, keep iterating, do the rapid iteration. I think that was a very, very valuable thing, because I ended up doing a lot of design and development for big operations readiness tests, like things that take 4 days, where we have all the flight operators going through the process of managing anomalies and prepping for launch and landing. And I had to run a ton of testbed shifts over and over and over, back to back, to design and iterate on these anomalous timelines that my colleagues and I got to develop. I got to be the testbed gremlin. That was great. That was my job title. But at the same time, I was pulling from a lot of the things that I'd learned from my NASA colleagues, who were, by the way, they were out of Johnson, which is culturally quite different from NASA JPL. I'd say JPL is much more planetary science oriented in general, culturally different. It's an FFRDC, but the principles of, well, how do you do this systems engineering? How do you do this test engineering and prove that these things work this way when they are integrated with hardware and software that might not be identical in a setting that might not be identical to your actual operating environment? If the test like you fly exceptions were just pages and pages and pages of explanations, and you had to be really rigorous about all of those. So kind of both of those, I really appreciated that. And I'm really glad that SpaceX had that input from the customer. That meant when I turned up at JPL, I was kind of both taking the requirements seriously, but I was also trying to probe, like, okay, well, why is this written the way that it is?
The nature of space, right, is that you're crossing through so many different realms of physics, right? And you have to engineer a system that works across those different realms of physics, some of which are very hard to emulate on the ground. Is that how you think about what's complicated about space, or do you think about it in a different way?
Something that I think is unique about aerospace, and definitely space in particular, is your system is not only subject to a unique set of conditions, but all of your systems are incredibly tightly coupled. Mm-hmm. And that is the way that AeroAstro, at least when I was an undergrad, really taught undergrads to think about this. Because I think at some universities, aerospace is in the mechanical department, and that makes sense sometimes that you could consider it a special case of mechanical, and sometimes that's the way we thought about it when I was learning about turbomachinery and the propulsion classes.
Right.
But in my opinion, it's about understanding the systems. It's about understanding your dependencies and your integrations, and about the way that slightly adjusting the frequency of your compressor in your jet engine can impact the structural acoustics of your airframe. And then when you stiffen it, it impacts the way that the software works, because it's accounting for a different input. And that's a thing that I think is really at the core. I gotta say, JPL actually invented a lot of this thinking back in the day, in the 50s and 60s.
Structured ways of systems thinking.
Right, structured ways of systems thinking. And I think these days that's regarded with a certain amount of, that's quaint. Oh, that's too confined. This is a framework. You can use that.
Right.
This is not trying to hem you in. This is trying to give you tools.
Right.
And sometimes if you're trying to hold too much to the tools, absolutely you can back yourself into confined spaces, and that's how you get a slowdown of innovation in the sector, for sure. But there's no point in reinventing those wheels.
Right.
Nature is going to happen.
Right.
Nature can't be fooled. It's going to come back, and you may as well have the tools and understand, well, why was this written the way that it was to manage that? So I think that's really the core.
This is what I talked about in robotics as well. Is robotics is a systems discipline, right? You're integrating hardware, software, AI. You're maybe not traversing through as many realms of physics, right, as in space, but you are building an integrated system that has to work.
Yeah.
And it has to work with people, right? So it has to work in an operational environment as well. And
that's easier, frankly. I mean, if you have an operational environment with a ton of radiation, for instance, like space, I was just talking to a friend of mine from Melogen at Symposium, and they're developing new materials to do rad hard shielding. People are so much harder. Oh my word. That's way less predictable. We know what radiation is like.
Yeah, I guess that's true. The physics is at least, there's math, right? Humans, there's less math.
In my language, that's always a test like you fly exception. You can have that. You can test it in what you think is a representative operational environment. And every single human being on the world, on this planet, is going to have a different interaction with your robots. So, that's just a perpetual test like you fly exception you have to account for.
Yeah. I thought when I went from large-scale distributed systems over to leading robotics at Amazon that I wasn't sure how much of my skills transferred. And I obviously had a lot of success in robotics, but it actually wasn't until like the last few weeks where I was realizing that one of my superpowers that I learned from large-scale distributed systems was how to change operating systems that are running 24/7 without breaking them, right? And the Amazon's global logistics network is a 24/7 operation. When I came in, one of the going-in theories was operators are going to resist change, so you need to make it like a burn the bridges moment where you just say we're going to do it this way instead of this way. So for instance, if we're going to put a new pack automation system in that's going to automate the packing of boxes, we have to take away the manual pack stations, otherwise the operators won't use it. Well, what this caused immediately was the operators who need to get their job done immediately put every requirement possible on the new system, right? Saying, okay, if you're going to burn the bridges, I need it to work this well, right? And they set the bar incredibly high because they needed to. Where if we said, more as we would do in software, let's run the new code alongside the old code, right? And we'll switch when we're confident it's working, or we'll switch some percentage of the traffic into the new software and some of it to the old software. Well, we did the same thing physically. I said, no, we're not going to take away let's find a building where we can afford the space where we can keep the pack stations and the new pack system. Well, now the operators were much more willing to try it. And even I remember sometime where we went all the way up to like couple weeks before peak because we really wanted to run through peak, right?
Right.
So that we could prove that it worked. And the operators would give us more chance to do it because they knew they had a fallback, right? Now in space, there aren't as many fallbacks. Like you get one shot, but.
Well, it depends on what you're talking about. I mean, at the moment, Starlink birds have, I don't remember. I've heard infant mortality rates of up to 20%. And that means, they jettison all these birds and like 20% just die. I don't know if 20% is the correct number. So, this is just what I've heard. But they can afford to do that. In other things, you can't. At this point, if you were to lose the trust of one of your operators, that operator is not going to be receptive to that packing machine hardly ever again.
Right, exactly. Trust is everything.
Yeah.
Trust is everything.
Starlink, you can do that because you have a million backups.
Right.
And you don't have to have a human being. Perseverance was wild because we were, as I said previously, we're doing these autonomous driving and drilling and sample thing operations. I was not as much on the surface end, but autonomous landing and separation of stages and a lot of really complex operations, and those all happen autonomously, and it's all operated with the compute power of a RAD 750. And by the way, these were really old RAD 750s because the reason Perseverance exists is because we had spare parts from Curiosity. It took a ton of heritage from Curiosity to de-risk it because we had one shot. There was no building another one, and if you lose, then that's more of a public trust matter, right?
Yeah.
If anything actually had gone wrong and we lost the mission, I don't know that we send anything to Mars ever again. I don't know that happens.
Yeah. Exactly.
Maybe not in my lifetime. And, we're working with a lot of duct tape and zip ties, metaphorical duct tape and zip ties, okay, except when they were not metaphorical.
What is the space-rated version of a zip tie?
They just make them out of plastic that doesn't outgas.
Okay. So there are zip ties. There
is such thing as a space-rated zip tie.
That's awesome.
But no, that was not. That was a metaphorical zip tie that I was talking about. Nothing left the planet that had anything that was not space rated on it, I promise. But we had to figure out a lot of things that had to work.
Yeah.
They absolutely had to work. And we knew it wasn't going to be something that comes back and we would collectively lose trust with everyone all at once. You probably had this interaction with a few different operators.
Yes.
And maybe there are some whose trust you have lost, but you were able to come back and work that over with other operators. And it sounds like you really grasped
and to
that.
your story about the empathizing with the NASA team on what's going on with that handle, right? Like operator empathy is such a key thing, like really understanding from their perspective, what do they care about? How can it fail? Fascinating. Well, I want to pivot to Mithril. I want to make sure we talk about what you're doing now. It sounds incredibly fascinating.
So Mithril at the moment is still a very small company, and I don't know that I would call it stealth. We probably should have stayed in stealth, but I ended up founding this company with Professor Zach Cordero right out of LGO, although for a while, as I said, it was just the two of us and we were figuring out where to go. And the technology is electrostatic actuation, so that's, the static electricity force where a balloon moves your hair around, maybe not yours, Brad, but that's what we channel and harness to be able to physically reshape a flexible reflector dish made of, at the moment, flexible gold molybdenum mesh that's used as standard for a lot of spacecraft, and we're pulling in different materials to figure out how to work with those. But that allows you to physically reshape your dish, and that lets you steer your beam and form your beam if you're using that for an antenna and radar system. And it lets you do that without the kind of crazy high power per gain, high power to gain ratio that you have with an electronically steered array. Did have a fun interaction with someone who said, oh yeah, but everything's phased arrays these days. And I'm like, phased arrays are the modern thing. I'm like, all right, well, so I was at this early warning radar station with the phased array face that was built in 1978. We've had these things since before the Cold War. I don't know that it's that different, but fundamentally, those you have trouble scaling. If you are trying to extend your ground radar to reach beyond LEO, or your in-space radar to reach from GEO down to Earth, or even beyond, if we're looking at cislunar and so on, you need a physically really big aperture, or you need a massive phased array, and your massive phased arrays, they take megawatts of power to be able to reach. And your massive dishes, we build them on the ground. We have existing ones that operate in space. They are really expensive to build, excruciatingly expensive, because your surface has to be incredibly precise, but it's really big. It's like if you have something the size of a volleyball court and you're controlling it to the thickness of a sheet of paper. It's kind of ridiculous. And that trade-off means that it's just always going to be expensive, or it's going to cost a ton of power. And that's why we have, in my opinion, that's driving a lot of stuff staying in low Earth orbit. It's one of the reasons we're a little bit constrained in the use of upper orbits. And it's frankly frustrating to me that nobody has figured out how to break the trade-off between these two things for decades. And what we do is we reshape that dish. We correct that surface. You no longer have to build it every time incredibly precisely, because you can correct that. And if you have a change in your use case, you can adjust and reshape accordingly. And so when I was getting to know Zach initially, I was not in his lab. I originally wasn't involved in the research, but I was really excited about this because I was seeing, okay, well, this changes many games. It changes the game for satellite communications beyond low Earth orbit, because it kills a lot of your complexity and your cost that is associated with having large enough apertures to make that possible. There's a particular type of microwave instrument that you could enable by having a large dish that's corrected to a really precise surface that enables microwave coverage through the whole depth of the atmosphere across thousands of mile wide scan sector. That's a 3D view of a hurricane that from space of the whole hurricane that we currently don't have. I was also, and more recently we've been seeing this as, people really want this to see orbits beyond LEO to be able to understand orbital maneuvering, possible orbital dogfighting. We've had that come out of Space Force, and interest in just keeping track of objects that we aren't very well aware of.
Right.
And that's been a really fascinating experience, just exploring and understanding, well, how many ways can we use this? Now, here's the rub, right? Being able to use something for a lot of things does not mean that you can cohesively address all of those market segments.
Right.
So then that comes into, well, how do you actually build that business?
Right.
And
where the economics really move the needle. Yep.
Right. And this is why I was grateful for the MBA experience, because went back to, okay, well, what are the customers telling us? And what I was hearing on the atmospheric radar side was kind of mixed. So Tomorrow.io, they're doing some cool stuff, but they're trying to do it like a lot of other people with a proliferated LEO constellation. Fine. What happens if we lose LEO? What happens if we have a catastrophic debris breakup in LEO? No one seems to be thinking about that. But they were 10 years ahead of us, and they have hundreds of millions of dollars in the bank. Fine. Maybe we don't compete on that end. We were getting kind of mixed signals, some strong interest in long-range SATCOM, and I'm starting to realize maybe in future that's a bit more of a market for us. Just because my husband was working on the Deep Space Network, actually. We were cross paths at JPL for a little bit. Deep Space Network is incredible, and it's still also mostly held together with zip ties and duct tape, and some super brilliant folks who are just underappreciated. But we're going to need more in-space hardware, more long-range capabilities. And then we got a lot of interest in people who are like, hold on a second, I want to be able to protect my spacecraft outside of LEO.
Right.
There's a lot of risk associated with orbital debris in LEO. It also just costs more if you have to keep replenishing your constellation with multiple launches. Maybe we operate with fewer spacecraft in a higher orbit, lower our OpEx, and wait, hold on, we can't keep track of it. We don't know what the risks are in these orbits. It's a little bit of there be dragons. And now we're starting to see interest in that. So focusing on the customer has been good. And then took me a long time to do this. People kept saying, all right, we'll just focus on one to begin with. I was like, but we have all of these applications. I want to do all of them. I will say the Activate folks have been, and some of our advisors at the company have been really, really helpful in pointing us, okay, no, let's figure out who do we talk to first? Who wants this first? Who's going in first? And that has ended up being the radar for space domain awareness, this capability to sense beyond low Earth orbit. And that's been where we've been focusing our development. We're currently hiring for a lead RF engineer. We may have already filled the position by the time this comes out, because this moves faster, obviously, than podcasts do. But that's a really critical position. And I think now that we've narrowed down this is who needs this first.
Right.
That's helping us give that direction.
I'm fascinated by this idea with physical AI that our AI systems are conforming our sensor. Right? Our eyes are tracking, they're focusing there. And so when we integrate AI with sensors that can adapt, right? We get this kind of compounding effect where we can, at a much cheaper level, and so that's what I think seems super interesting about your capability, right? Is AI is going to make it so that we can modify this sensor to look at whatever we need to look at, right?
I'm very excited about integrating that. First off, I think machine learning is probably going to be the best way to do our closed loop controls, because anytime you have something flexible, it's a chaotic system, so it's an ideal machine learning problem. But quite apart from that, if you spot something really far away, you should be able to focus and start directing all your signal power on it, and then you get into the tip and cue, and then you can start directing other things. Like, you might see something that is approaching you, and your lens adjusts to focus on it. You narrow your focus, and you see, oh, okay, that is a ball that is coming at me, and then you integrate another sensor, and you reach out and catch it. We're not catching balls in space, but that's the idea.
Well, look, this has been incredibly fascinating, amazing career you've had. Super excited to keep following the progress at Mithril, and thank you for taking the time.
This has been so cool to catch up, Brad. I'm really excited about what you guys are doing at Cobot, and I appreciate the systems thinking that you're bringing to it, because I think that gets missed. And I'm excited to see what you guys do.
Awesome. Thank you so much.